been really amazing, and thank you, Anna, because most of the concepts that you have introduced, I will make you use, so I don't have to start with these concepts. In any case, as we know that you have very different backgrounds, I decided to make first lesson, well, all the lessons, but especially this one, very, very didactic in the sense that we will start from very first basic principles. So I'm sorry to those that are specialists in applied mathematics or dynamical systems because we will construct everything. As you see, here you see Kuramoto model. We will reach the Kuramoto model at the very end of the class, okay? First, let me introduce myself as one of the organizers of this school with Cristina. I'm a PhD in physics from the University of Zaragoza in 2006. This is my alma mater, and it's where I'm currently now. After my PhD, I went to different places for postdoc, especially to, okay, I don't know. I didn't make any postdoc. No postdoc. Okay, I don't know what's going on with it. I think it's blocked. Now, yes, postdoc. Okay. So in Italy and also in Tarragona, and then I went to Madrid. So after some years, I became lecturer, and finally came back to my university as Ramon y Cajal, sorry. So it's a very good fellow for this course, Ramon y Cajal Fellow. And finally, I'm now full professor in the University of Zaragoza. So this is more or less my trajectory. And what's more important to you is not my trajectory, but my group, which is this, with this funny name, Gotham Lab, which is the group of theoretical and applied modeling. And modeling is the important part. And what we try to model, well, myself and a lot of people that work in the lab, not for a physical one, obviously. If you are experimentalist, it's not quite a lot. Is that we try to analyze the emergence of collective phenomena in large ensembles of coupled units. And these units can be neurons, these units can be people, these units can be cars, whatever, or packets in the internet. And in particular, we focus on very, very different collective phenomena. For instance, we focus on the transmission of culture and the spread of information in social systems, how we collect culture and adapt our lives to spread the voice. Cooperation, the evolutionary dynamics of this item that helps us to survive as a society, and not only people, but also animals and plants. Congestion in communication systems, for instance, the internet, how this emerged as a product of the different trajectories of different packets navigating these systems. Epidemic dynamics, which is focus a lot of work nowadays in my lab. I will talk about this in the colloquium. And finally, synchronization, okay, which is the focus of this course. And in particular, we will focus on this particular topic. So let's start with this course, and let's go, as I said in the introduction, with the introduction to the phenomenon of synchronization and also the Kuramoto model. So let's start with the most basic dynamical system that you can have. This is a time-continuous dynamical system, only one variable, okay, x. And this, you have a function, which is f, which governs the dynamics, the evolution of this variable, okay? So this is an example of a nonlinear dynamical system. Evidently, is nonlinear because you have this sinus function. And this is very simple because even we can derive the solution analytically, okay? We can integrate it, okay? But the usual form we tackle the analysis of a dynamical system is not to consider the analytical solution, because typically there is no analytical solution, but to inspect what happened in the phase portrait of the system, okay? So for one-dimensional systems, it's really easy. You just have to plot the function f, the sinus in this case, as a function of the variable. And you have, obviously, the plot of the sinus, okay? And then what we focus is in the question about if there are fixed points of the dynamics. And a fixed point is a point in which this function f is equal to 0, because this means that the derivative of x is equal to 0. Here, obviously, we have points periodically. Every p times we have a 0. And then, now the next question is about the stability of these fixed points, okay? And it's very simple to analyze in this kind of one-dimensional systems the stability, because if you know what happened in between the two fixed points, you can see where the velocity points, okay? For instance, you see that here you have negative velocity, so the flow goes towards the left, and here in the positive part you have the flow going towards the right part of the line, okay? So for those points like this one in which the flows departs from it, we can say they are unstable. And from those points in which the flow points into the fixed point, we can say they are stable. So we have two kinds of points. You can also, and you must, assess the stability by looking at the derivative, okay? So you just take the function f here, the sinus, consider the derivative here, the cosine, and evaluate the derivative in each of the fixed points of the solution. And for those unstable, you will see that the derivative is positive, and for those stable, you see that the derivative is negative, okay? Same. And that's all, okay? That's all we need. Now we focus to variables that are periodic, because we are interested in oscillators. And each oscillator will be described as a phase variable. In a phase variable, the situation is the same, okay? Here, I have just changed the name x by theta, okay? But you have one additional constraint, which is that the function, the velocity function, must be periodic. Otherwise, we cannot say that this point, minus pi, corresponds to this one, okay? Okay, so let's start. We are just the mathematics we need to know, okay? We will cover the first thing, non-uniform oscillator, one single oscillator. Then we will move to synchronization of two oscillators. And finally, we will go to the Kuramoto model. We will make the big jump from 2 to n, being n 1 million, for instance, okay? So let's start with non-uniform oscillators. This is a uniform oscillator, okay? It is the derivative of the angle is equal to a constant, here called omega, because it's the frequency, the natural frequency of this oscillator. And it's very boring, because we have this phase portent, we have the velocity as a function of the angle is just this, omega, constant, nothing more. Is there any fixed point here? No. Everybody, no. No, because this function is constant and you don't have any crossing with the theta dot equal to 0, okay? So there are no fixed points, and also we know that the period of the oscillations here is just 2 pi divided by omega, okay? Now let's make it non-uniform, okay? And we put this nonlinear term, again the sinus, which is weighted by this A, okay? A is a parameter that you control. If A is equal to 0, then you have a uniform oscillator, okay? If you increase the value of A, this means that the oscillator becomes more nonlinear, okay? So for A small, what the nonlinear terms do is just to modulate a little bit the former line, omega, okay? So we have that the oscillator goes a little bit faster than omega here and a little bit slower than omega here. There are any fixed point in this case? No. No, still. No. Okay? What's sure is that the period is not 2p divided by omega. Okay? We have to calculate it. We will calculate it. If we increase A, what happens is this. You can increase A a little bit more, and you find this. Still no fixed points. Okay? What you do is just to increase the heterogeneity of the velocity. Here is much faster than omega, and here is much slower than omega, okay? Because of the function, because of the modulation. And finally, if you increase a little bit more A, now there are fixed points here. Yes, 2 fixed points. And what is this? Which kind of bifurcation from the lot of bifurcations that Anna introduced in the previous lecture? It's a saddle node. Because you have a situation in which the qualitative change, which is the important thing, is no fixed point, new fixed points, in particular 2 fixed points. So previous to the bifurcation, to the saddle node bifurcation, we didn't have any fixed points. Now we have 2 fixed points, okay, that are born, one stable and the other unstable. It's typically the same, always, okay? So we can evaluate the derivative. Here the derivative is negative, so this is stable. The derivative is positive, so this is unstable, and that's all, okay? And there is a saddle node bifurcation when this A equals to the value of omega, okay? What happened is that we have 3 regimes. Previous the bifurcation, after the bifurcation. In the first previous the bifurcation, we don't have any fixed point, and we have a non-homogeneous oscillation with a fast region and a slow, even slower because of zoom, region in which, again, fast, slow, but we have these oscillations. In this case, we have a single fixed point because it's just the bifurcation point, the point in which 2 solutions emerge, in which we have a deviation from this new fixed point, makes you make this one excursion towards the circle. And finally, we have the situation with 2 fixed points in which if you start here, you finish in the stable going upward, and if you start here, you finish again in the same stable solution going downwards, okay? Because of these 2 branches. Okay, so very, very easy. The period, I promise you to calculate the period. The period is very easy to calculate. Just consider that the period is the integral from 0 to t, the period of dt. Make the variable change, so you make use of the equation that we have here, okay? Finally, you put the equation, you have changed, this is the Jacobian actually, this is 0 to pi, and you can do this equation in a compact way, and you can evaluate also 0 and 2 pi, and you finally obtain the expression for the period. And as you see, if this is the period, this is the frequency. This is the frequency, okay, the mean frequency, the effective frequency of the system as a function of A. If A is equal to 0, we recover that the frequency is equal to omega, the uniform case. If A starts to increase, what happens is that the effective frequency starts to decrease, okay? And in fact, what we can plot is a bifurcation diagram in which we plot the effective frequency divided by the natural one. So for A equal to 0 is equal 1, as a function of A divided by omega, which is the critical value. So the bifurcation takes place here. So here we have the situation without any fixed point, and here we have the situation with 2 fixed points. The important thing is what happened here. So what you can do is to plot or to consider that A is very, very, very close to omega. So omega minus A is very small. If you do this, and you can make the derivation very easily, but by considering that omega to the square minus A to the square is omega minus I times omega plus I, you find this behavior, which is typically from a saddle node bifurcation, the typical behavior of the frequency, okay, with this exponent 1/2 that's happened here, which is just this behavior close to the bifurcation, okay? Any question about this problem? It's very easy, right? Super easy. Okay. Again, the important thing, a saddle node, before happening a saddle node, the system starts to have a very, very, very slow dynamics in some part of the trajectory. And that's why these kind of bifurcations are called ghost bifurcations, because you don't see anything, you don't see any qualitative change, but just before the bifurcation, you start to observe that something is going to happen, okay? Because the trajectory is like this one that I'm going to show. Okay, so you have here a region in which theta barely varies, okay? So it stays here because you have to stay a lot of time here in order to go to larger thetas, okay? This is the typical bottleneck region before a saddle node bifurcation. Okay, so let's go to another problem, which is also very simple, but we start to make another ingredient, okay, to put another ingredient into the equation, which is the synchronization with an external stimulus. So typically, we are going to have this equation, okay? This equation, which is very, very similar to the one we have introduced just before. The situation is the following. We have a system. Let's consider it's a firefly, okay? And this firefly, this little friend, has a variable, which is theta, okay? Our angular, our phase. And this firefly is in contact with a tree, which is full of fireflies. In this tree, synchronization takes place. You can observe it. This is the typical synchronization picture in which you have these synchronized flashings of the fireflies. And this firefly is far away the tree and is looking to the tree, okay? So we can consider that this phase, which is the phase of all the fireflies, because they are synchronized, is flashing with some frequency capital omega, okay? And as I said, the firefly received the input from the tree, okay? And this equation is governing this interaction. The influence that this tree has on the firefly is captured by this equation, okay? As you see, the question is if the firefly is going to synchronize with the rhythm of the tree, with this capital omega, okay? So let's start our evaluation. The assumption, as I said, is that the bulk, the tree, remains completely unaltered, okay? They don't see the firefly. They continue to flash with some capital omega frequency. And we are going to consider the phase difference between the phase of the tree minus the phase of the firefly, okay? This is our new variable. If we do this, okay, and we introduce this change of variable in our equation, what we obtain is the following equation. The derivative of the new variable phi is equal to this derivative, which obviously is omega, because we have assumed that the derivative of the collective phase is constant, minus this, which is going to be this equation, this part of the equation. So we have this equation, okay? Okay, we have three parameters, capital omega, omega, and A, which is the coupling. We can try to reduce the number of parameters. This is a typical thing in dynamical systems. Try to reduce the number of parameters, and to do this, we can adimensionalize the system, okay? So we can do this to change of variables. We can, in fact, we divide the equation by A, so this induced to redefine the time, also to introduce a new parameter, which is this omega tilde, which is just the difference between the capital omega and omega divided by the strength of the coupling. And with this change of variables, we have an equation with a single parameter. And have you met this equation before? It's the same equation we have for a single oscillator. But here A is equal to 1. Okay? So it's the very same equation we have before for a one oscillator. Now we have the same equation with A equal to 1 for these two coupled systems, the firefly and the bulk and the tree. Okay, so everything is the same. Everything is the same. We are going to find different solutions depending on the value of omega tilde. And that's all. A is equal to 1. And we know that if omega tilde is equal to 1, a bifurcation will occur. Let's analyze it again, okay? Also, it's the same story. Obviously, if omega tilde is equal to 0, so these two are equal, or A is going to infinity, but it's more realistic that capital omega minus omega is equal to 0, we have this picture, okay? We have that the evolution of phi is minus the sign of phi, because this is 0, and this is plotted here. We have two fixed points. One is stable, the central one, and the other The other two, but it's only one because it's a periodic system, is unstable. And if this is the stable one, this means that there is full synchronization. Obviously, it's full synchronization because the frequency, the natural frequency of the firefly and the natural frequency of the tree are the same. Okay. What happens when we increase omega tilde? If we increase omega tilde, we have, again, two solutions. Okay, still two solutions. But now what we see is that the stable solution is for a phi, which is non-zero. This means that the phase here is, in terms of phi, there is some phase locking, which means that the phases of the firefly and the tree are not the same, but the frequency is the same. Okay? And obviously, if we increase the value of omega tilde, a saddle node bifurcation occurs in the inverse order, and we lose the two solutions, and we don't have any solution. Okay? We can do the saddle node in both directions. Okay. What does it mean that we can increase omega tilde? Okay. Let's go to the expression. Okay? This is omega tilde. And imagine that we are in a situation in which omega is here. We have plot here an interval, which is omega minus a, omega plus a. And here we have the capital omega, which is the frequency of the tree. In this case, there is full synchronization. If omega tilde is here, we have phase locking, frequency synchronization. The angles are not the same, but they pace at the same frequency. And finally, if we have this situation, no solution at all. Okay? Okay. What can we do? Imagine that the difference in the frequencies, the natural frequency of the firefly and the frequency of the tree is fixed. So what we can do is to increase the coupling. If we increase the coupling, we increase the range of entrainment, and what we have is, again, and recover the situation in which there is some synchronization, frequency synchronization between the firefly and the tree. Okay, so we can adjust this value of the coupling in order to have, again, synchronization, which is the essence of what we are going to study in the next days. And this is the bifurcation diagram. We have the coupling A here. We have omega, which is the natural frequency of our firefly, of our friend. If omega is exactly equal to capital omega, we have full synchronization. The phases are the same, the frequency are the same. And then we can have the other phenomenon, which is qualitatively the same, in which the phases are not the same, but the frequency is, and what we have inside this cone. And outside this cone, what we have is no synchronization, no fixed points. And this border, these yellow lines, are the borders in which the saddle node bifurcation occurs. Okay? So if we are here, if we have a natural frequency which is not equal to the capital one, what we have to do is to go at least to a value of A equal to this in order to enter into the region in which there is synchronization. Okay? Any question? Yeah. If you go, this is the minimum value of A that you need. If you increase this, then you will enter into the region of frequency synchronization. Not full synchronization, but frequency synchronization. Okay? And this is the cone. Any other question? Yeah? No meaning. A is just a weight of the coupling between them. Yeah. Okay, so let's continue. And now start to consider this. Because we have considered that the bulk, the tree, is already synchronized. But the question is how these thousands of fireflies get synchronized. Okay? So this is our problem, the synchronization in a large ensemble of coupled units. And we are going to start by studying synchronization, which is obviously the core or one of the most important topics in this school, which is because it's at the core of the functioning of our brain, not only the brain, also other systems. And we are going to start thinking about synchronization by studying, again, two firefly. This is a different problem because before it was a firefly that was driven by the input of a tree, but the tree was totally unaltered by the firefly. Now the situation is different because, again, we have two systems, but these two systems are coupled together. There are two fireflies, 1 and 2, and one see each other, okay? One sees 2, 2 sees 1. And in fact, the influence between A and 1, the influence that 2 has on 1 is weighted by A, and the influence that 1 has on 2 is weighted by B. They can be equal, but in order to make it more general, let's assume that A and B are different, okay? So now we have a two-dimensional system, a real two-dimensional system, and we have to study if there is some synchronization in this, with these two fireflies. So, to this end, we have to analyze the system as if we have two oscillators in the unit circle. So, obviously, omega 1 and omega 2 are totally different. Okay, each firefly is different. Otherwise, they will synchronize. And so, this oscillator make this with velocity omega 1, and this other oscillator make the run across the circle with velocity omega 2. To analyze this, we are going to consider a new variable, okay? We are going to change the variables, and we are going to focus on the difference between theta 1 and theta 2. Why the difference? Because we are interested in solutions that are synchronized. And if they are synchronized, this will mean that, for instance, theta 1 will be to theta 2. Okay, so phi will be equal to 0, okay, for instance. Okay, if we do that, we can construct the evolution equations just by subtracting this to this, okay? So the derivative of the new variable is the derivative of the first variable minus the derivative of the second variable. If we do this, with this equation, we have this new equation. Again, have you seen this equation before? Yes. This equation, again, is the very same equation, has the very same functional form as the first equation we have studied in this class, okay? So we know everything. We know that depending on the value of this difference between the frequencies and the value of this sum of the couplings, which play the role omega 1 minus omega 2 play the same role as omega, and A plus B play the same role as A, we will have this kind of solutions we are interested in which the phi variable has some fixed points, and these fixed points imply that the two fireflies synchronize their frequencies. Okay, so let's analyze it again. And we know that we impose the stationary solution, okay? So we impose that this equation is equal to 0, and if you impose that this is equal to 0, you can derive the condition and the expression for the stationary solutions, okay? And you see that the sinus of the stationary point have to be equal to this. Obviously, the stationary solutions are 2, because 2 possible angles, phi star, has solution this expression, okay? And this is the, yeah. Sorry? Probably yes. No, it's okay, because it's minus here. So if you put this equal to 0, then you have omega 1 minus omega 2 and divide by A. Yeah, but you pass it to the other part. Omega 1. No, because here you have to change the phase. Here you have to change, and this is minus A. Okay. No, it can be. I mean, even if you have do these lessons many times, it's not the case, but you will still have typos. Okay, so you know, okay, you have to, in order to have the same here, you have to put theta 1 minus theta 2, so you have to change the order, so here you have a minus, okay? So it's okay. These are the solutions, okay, two solutions, okay, this one, and these two solutions fulfill that the sinus of these two angles are equal to this. Okay, one is stable and the other is unstable. Nothing new today. So, can we derive the frequency, the agreement to the new frequency? Remember that this fixed point means that the two variables, the two angles remain, the difference between the two angles remain constant. This means that the angles are not the same, but the frequency is the same. So the frequency will be obviously either, if you can calculate it as theta 1 dot or theta 2 dot. Let's go to theta 2 dot, okay? And if you put here omega 2 plus b, and this is the sinus of phi, because we have this, you substitute this expression here, and you will have theta dot, which is the expression for the effective frequency. Again, as in the postdoc. Yes, no, yes, okay. Yes, thank you very much, Anna, thank you. So this is omega star, and you have this expression. Look to this expression. This is the frequency, the compromise frequency. It's neither omega 2 nor omega 1. If A and B are equal, okay, this omega star would be just omega 1 plus omega 2 divided by 2, the average. Okay? If we are identical, I mean democracy, then the omega star will be just the average. But if A and B are different, then omega star will be much closer to the one that dominates more to the other. Okay? And in fact, you can see this compromise frequency, okay, omega star, in this case is closer to omega 2 because surely A is larger than B. 2 influence more to 1 than the influence of 1 to 2. Okay? Okay, so this is the compromise frequency. This is the picture, not in the phase space of theta 1 and theta 2, not in the phase space of phi. And you see the two solutions here. This is the solution which is stable. You see that the variables are not the same because otherwise will be here. But they have the same velocity, so they have these lines, okay? The other solution, which is this dotted, corresponds to the solution which is unstable. You don't see this solution because it's unstable, okay? The thing is, when this solution will disappear, because we know, because we have studied this system before, that there is some point in which a saddle node bifurcation happens. And the thing is that here, in order to this solution to be satisfied, this is a sinus. So this quantity should have a modulus which is less than 1. If this quantity have a modulus larger than 1, it cannot be a sinus of a function because the sinus is between -1 and 1. So it can happen, for instance, that the difference between the two fireflies, omega 1 and omega 2, is large enough that we have a quantity which is larger than 1, okay? If this difference, the modulus of the difference is larger, in fact, than this A plus B, this is larger than 1, and then a saddle node bifurcation occurs, okay? And we lose the frequency, the compromise frequency, we lose everything. There is no possibility of synchronization. Okay, this is for 2. What happens if we have this much more n coupled fireflies? Then the question is that we have to go to the Kuramoto model. Okay, this is Yoshiki Kuramoto in the Kyoto University, and in 1975 proposed a model to treat this n-coupled fireflies or n-coupled oscillator interaction and the emergence of synchronization. Now, be aware that we are making a jump from 2 fireflies to n-coupled fireflies, okay? And this is a very, very important jump, okay? But we will do it, and we will do it in 15 minutes or less. So we can go to lunch and discuss about Kuramoto. So the Kuramoto model is just a collection of phase oscillators, again, from theta 1, theta 2, and theta n, okay? We assume that the equation for each oscillator is governed, in isolation, is governed by this constant frequency. So a uniform oscillator, a collection of uniform oscillators, omega, with each one having a different natural frequency, omega I. These natural frequencies are assigned because n is very, very large. We are working in the thermodynamic limit, okay, in the n going to infinity limit. It's assigned from a frequency distribution that, and this is very important, because this is the clue, has to be unimodal. For instance, think about a Lorentzian, a Gaussian, whatever, and symmetric around the mean, okay? Lorentzian, a Gaussian. And this is not a restriction because you can always change the variable, okay? We will consider that the mean is equal to 0, okay? But this is not a restriction. I mean, you can redefine the variables in order to have an average frequency 0, okay? But the important thing is that this frequency distribution that you use to assign the natural frequencies of each oscillator are unimodal and symmetric around the mean. Okay. The next assumption, which is not an assumption, I mean, it's something that was present in the Kuramoto model, is that all the oscillators are coupled all to all. Okay? Each oscillator is coupled to the remaining n-1 oscillators. And how they are coupled? Okay. You are expert already in this kind of equations. So the way they are coupled is just by a nonlinear term, which is just the sign of the phase difference. Okay, capturing that if you are beyond me, I will speed up. If you are behind, I will slow down. Okay, I will try to go with you, and this is captured by this sinusoidal coupling. Also important that this coupling, which goes from 1 to n, because you have to take into account for each oscillator the interaction with the remaining oscillators, is weighted by this number k, okay? N is just the total number of oscillators, and k is the true control parameter, okay? If k is equal to 0, what we have is just a collection of uniform oscillators. If we start to increase k, what happens is that you pass from a situation in which each oscillator, the color accounts for the natural frequency, for instance. Each oscillator is in a different place at each time step, obviously, because they move around the circle, and you end up increasing k in this situation in which all the oscillators start to group and try to go with the same frequency. Okay, this is an example of the Kuramoto model, okay, but with only 5 oscillators. Okay, I don't have sound, so you have the metronomes. They have slightly the same frequency, and now you see you don't see anything. But the coupling, each movement is influenced the others because of these two cans that move because of the coupling. And now, after a while, you start to listen to they have synchronized, okay? You see why I didn't need the sound. Okay, so this is a very nice example of 5 oscillators. You can adjust the metronome to have a frequency, okay? That are coupled all to all because of this piece of wood, which is just on the top of 2 cans, and you attain this state in which all the oscillators pace at the same rhythm. Okay, so let's go back to our equation. Now the thing is how to quantify this transition. You here now have a real transition, okay? The other was a picture. Now you have the distribution of a collection of 200 oscillators, okay? The color here is the natural frequency, and you see what happens when the coupling is small, and when you start increasing the coupling, you see that this synchronization cloud is formed. And finally, if you have large enough coupling, what you have is that the cloud is stretched, okay? And all the oscillators, almost all the oscillators, are inside this cloud. Be aware that those oscillators that are not in the cloud, here and here, correspond to these frequencies, the frequencies that are much far apart from the mean frequency. The mean frequency here is 0, okay? How can we quantify? This is an observation, okay? This is an observation. How we quantify the degree of synchronization in the system? And now, as Christina introduced, we have the Kuramoto order parameter. The Kuramoto order parameter is the following. Consider, for instance, here, each oscillator with the phase, theta j here, and consider this complex number, which is a phasor, okay? And this is just the exponential of the imaginary part of theta j, okay? Now consider the sum. All the oscillators have associated a phasor, and we consider the sum. And in fact, we consider the average, okay? We sum across all the oscillators and divide by n. Obviously, this is a complex number, which have modulus and phase. But the thing is that if we are here in this situation, the sum is totally destructive, okay? You always find, for each oscillator, you find another one which is in the opposite part. So at the end, every pairs of this kind cancel out, and you have a sum which is 0. But if you go to this situation, the sum of all these phasors is constructive. And then you have a complex number, of course, with a modulus which is not 1, but is very large, close to 1, okay? And this is the complex number that we are dealing with, and this modulus is what is telling us if we are in a situation like this, because this modulus will be 0, or if we are in a situation like this, because the modulus will be really large. And if you study the evolution of the modulus of this complex number as a function of k, what you find is this transition. And this is a transition, and this is, as we will see, a kind of bifurcation, okay? Because it's not, and this is very, very important, it's not that as k is larger than 0, you have synchronization. No, you don't have synchronization until you reach this value, okay, which is the synchronization threshold, the synchronization onset. Before the synchronization onset, what you find is totally incoherent states. Everybody is going more or less at their natural frequencies. From this point on, what you find is the emergence of the synchronized state. And for large enough couplings, what you have is the state of full synchronization, okay? And we are interested in this part, in the synchronization onset, which is the minimum coupling that we need to put in our system in order to have synchronization, okay? And this is what we are going to do in 5 minutes. Only 5 minutes. Well, 7 minutes to be precise. Okay, so this is the Kuramoto order parameter. Everybody understands what's going with this parameter? Okay, this is our Kuramoto equation. I'm going to do a trick, which is the single trick I'm going to do, okay? Which is just multiply this and this, the two parts, by, well, you will see here, by this number, a to the minus theta. The exponential of obviously the imaginary number and minus e. I have just multiplied this part and this part. In this part is here and this part is here, okay? Nothing more, nothing less. Now, the magic appears. This is a complex number, okay? And we take the imaginary part of the complex number. The imaginary part of both sides, here obviously is r times the sinus of phi minus theta I, and here we have the sum of the sinus, okay? And now we see that this part is identical to this part. You see, this part, the imaginary part of this expression, this part is exactly identical to the coupling term in the Kuramoto model. You see it? Yeah.
Shouldn't we sum the exponentials when we multiply?
So you have the sum of the cosine plus I, sum, there is no product, so it's the sinus.
Yeah, but there's a negative subtraction in the exponential indices. If we multiply, shouldn't be an addition?
¿Dónde?
And sum?
Where? Can you point? Yes, yes.
How we put here?
Mm-hmm.
Shouldn't it be a sum here, not a...
No. It's just the multiplication. We have multiplied both terms by multiplied. You multiplied the equation, which is sorry. Oh. Okay, you multiply this equation, this, and this. Okay. Any other question? Now it's not 7 minutes. Now it's 9 minutes. It's okay? You can do as a homework with one caipirinha. Okay, so the magic now is going to happen, okay? These two parts are equivalent, so let's substitute this part by this part. And what we have is this equation, and this equation is magic. Because now what we have, and I just recommend to read this paper, which is really, really nice paper by Strogatz about this equation. You don't have now the coupling, apparently, okay? You have it, but apparently you don't have the coupling with the rest of the oscillators. You have that the velocity of oscillator I is equal to its natural frequency, and then a coupling term with some mean field, which is created by the bulk, okay, but no J, etc., times the sinus of this average phase that you have in your system minus your phase. So apparently, we have decoupled all the dynamics, and we have a collection of equations. Obviously, we have n equations, each equation for each oscillator, in which you have the same form, okay? Moreover, you can choose to have the average phase equal to 0. This is very simple because it's just to make a change in the reference frame, okay? Because this is the average phase of the system, and you can put initially the phases, the average phase equal to 0, and the average phase doesn't change. And we have to study this equation. Now there is no Homer Simpson. But you know this equation. It's the same equation that we had at the very beginning of the lesson, the very same. So what we know is that in the steady state, if we impose that theta I is equal to 0, the derivative of this theta I is equal to 0, we have, again, this condition, okay? You can change K R by A if you want. Omega I is omega, but the same condition for the locking that we had before holds. Again, the sinus is something that has to be restricted between +1 and -1. So this solution can be achieved only by some set of oscillators. In particular, those oscillators that have a frequency, a natural frequency, whose modulus is less than, I catch the fly? No. Is less than K to R star, will be in the synchronization cloud, will satisfy this equation. For those oscillators with a natural frequency with modulus larger than this, they will be drifting. Okay, so we have two classes of oscillators, those that are drifting, that are not synchronized, that don't fulfill this equation because omega I is so large that cannot fulfill this relation, and those whose natural frequencies are less than this threshold, so that they can be in this cloud, in the party, in the synchronized party. Okay? Okay, let's go a little bit further. How can we monitor, now that we know that two kinds of solutions appear, those lock and those drifting, can we derive the behavior of the Kuramoto parameter in order especially to derive this point? Okay, let's do it. We take into consideration the Kuramoto order parameter, which is just the sum across all the oscillators of the phasors. But now we do the sum in two parts. The sum of those oscillators that are locked plus the sum of those oscillators that are drifting. I just divided, okay, this is a sum of all the oscillators. Okay, all the oscillators that are locked go in this sum, and all the oscillators that are not locked goes into the other sum, okay? Nothing more. Okay, but because they are drifting, so again, it's the same situation as here. You will always find a couple that is just on the other side of the circle. So the sum will cancel out. And you can do this because we are in the thermodynamic limit. We are going to n being very, very, very large. So we have this sum, the sum for all the oscillators that are locked. How I made this sum? Okay, since I know that all these oscillators have a natural frequency between minus chi r star and plus chi r star, because otherwise they are not here, what I do is the sum, and I do the integration. This is the weight, because I know that there is a different number of oscillators depending on the frequency, so I have to weight by g the omega, and this is just the term that I want to sum. And I do the sum. This sum is an imaginary number, so it has real part and imaginary part. This is the real part with the cosine, and this is the imaginary part with the sine. Nothing more, nothing less. Now, I substitute the sine by the omega divided by chi r star, which is the condition for locking. Okay? Nothing more, nothing less. And this is 0. Why? Because, remember, this distribution is unimodal and symmetric with respect to 0. So this is a function which is, g omega is a function which is symmetric, and the other is not symmetric. One is even and the other is uneven. Okay? So the result of this integral, because it's between the symmetric interval, is equal to 0. Okay, so we have the first integral. Now I make a change of variables, which is very simple because it's just changing omega by theta. And we have this new integral. And this is the integral I have to evaluate. This is the integral that satisfies the Kuramoto order parameter. This is here as a function of k, which is here. The problem is that this is a self-consistent equation. I don't have the solution here because in order to have R, I have R here and I have R here. Okay? Obviously, there is a solution that always exists for any value of k. Any of you can tell me which value of R is always a solution of this equation? 0, exactly. 0, if I put 0 here and 0 here, everything is satisfied. 0 is the trivial solution. 0 means that there is no synchronization. So, in this system, the solution with no synchronization is always a solution. The problem is the only solution? And if not, is the stable solution? Okay, so we are going to look to a different solution, the non-trivial solution. Because I'm interested in the non-trivial solution, then I can do this, okay, and put here a 1, and here just this. And then, now, I have to solve this equation. The thing is that it's impossible to solve this equation, okay? But, as usual, if I'm interested in this point, not in the whole diagram, but in this point, then I can make an assumption. And the assumption is that close to the limit, close to here, the order parameter is larger than 0, but is almost 0. Okay? It's not 0, but is, as physics we say, epsilon. Okay? And if we do that, we can change the argument of this function by 0, because here is R star. So if I do this, here I have a constant, and the equation that I have to study is this. And this is just an integral. It's the integral of the square of the cosines between minus p half and plus p half. And this is an integral that I can do. The result is p divided by 2, and then I have the threshold. And this is the threshold for synchronization in the Kuramoto model. That, as promised, it was 9 minutes because of the question, okay? So this is a very, very important result because it tells you what is the precise value of the coupling between fireflies, between oscillators. Let's start talking about oscillators that you need in order to make the incoherent solution, which is always a solution, unstable, so that the synchronized states show up as the unique stable solution, okay? That's why this is a synchronization in the mean field limit, okay? It's important that you check the expression. It's 2 is 2 always. Pi is pi always. What happens is that the only contribution of the system is this G0, which is the fraction of oscillators whose natural frequency is 0. Or if you want, the fraction of oscillators whose natural frequency is the average one, okay? The more oscillators that initially have a natural frequency equal to the mean, the lower the critical threshold. Why? Because at the very, very beginning, I have already a large number of oscillators that pays to the frequency which is going to be the synchronization frequency, the compromise frequency, if you want, okay? That's why it has this expression. Okay, so this is what we have studied today, and tomorrow we will cover this, which is slightly the same, but now I have removed a lot of links, which is much more complicated, okay? And this is synchronization of networks. So this is what we are going to do tomorrow. Okay, thank you. Any question before lunch? Jordi, vaya.
So if you said that A and K are only parameters, so
I don't understand you. Please don't do it.
You said that A and K are only parameters for the equations, right? So
AK.
A multiplying the signs of...
In which equation?
The first equation of theta equals to omega, theta point dot, plus A sine of theta 1 minus theta 2.
Okay.
Okay. So, but I mean, if we see a biological system, we can like extract the A of the system only by looking to the systems, or only by fitting with the data.
Okay. This is a more general question on the Kuramoto model. First, two answers. The first one, the Kuramoto model has no physical interpretation at all. The closest interpretation that have is a Josephson junction, but I mean, this is another story. The Kuramoto model is the minimal model in which you have this kind of critical threshold. So what we do here is to understand the synchronization phenomenon by inspecting a model which is the minimal one in which you have this kind of threshold phenomenon of bifurcation. If you want to go to realistic systems, then you have to increase the complexity, okay? And if you, considering that this model, for instance, is something that you can use to model in a reliable way a situation, yes, you can obtain from the data, you can infer and make some calibration the parameters of a model, okay? This is pretty similar to what we do in epidemic models, in which we show a curve, and if you have a model, a baseline model, which is, let's say, a simple one, an SIR, you can derive, for instance, the probability of infection and the probability of recovery, or other kind of models that I think Christina will discuss, more refined, in which you have data, and from the time series analysis, you can derive some constant of the model. Okay, you can do it. This is calibration, and typically you use Bayesian inference, for instance, in order to have the best fit to what is observed of your model, the best fit to reality, okay? But in this kind of systems, the important thing is the phenomenology. Okay, the phenomenology is similar to more complicated systems, like like in neurons, for instance, and that's why we choose this system in order to present you the problem of synchronization. Ah, yeah.
Doesn't represent the intensity of the laser. It's just a variable, it's abstract. You see a bifurcation diagram, but then when you go to study a physical variable, you sometimes see the same thing.
Let me tell a story, Cristina, which is, I think, more important than the logistic and the Kuramoto. Lorentz. The Lorentz model was a model which is 3 variables, okay? And it was, Lorentz was trying to show that the typical way of forecasting was totally absurd, okay? So he devised this model, which is for the problem of convection. But when he presented the model to the people working in fluid dynamics and meteorology, they say, okay, Edward, this is not realistic. I mean, this is something, this is very nice, but it's not realistic. And this was the most important model in order to found the field of chaos. So it's one thing of the models, the low-dimensional models like these ones, or Lorentz or logistic, is that they capture, in a very simple way, some phenomenon that you observe in reality. But if you are going to calibrate, if you are going to infer parameters, you can do it. But they will be useless in order to anticipate, to make predictions. Okay, so these are 2 faces of the same coin.
Okay, so we made 2 assumptions.
More than 2 assumptions.
More, yeah.
But you didn't realize.
Yeah. I mean, 2 assumptions. First is that we are ignoring the environment, so there is no external force in the system. And all the oscillators contribute the same way, so they communicate in the same way with the others. And I would like to know if there are like several fields that study the Kuramoto model in those conditions, that external forces and different contributions, and what is the application of the Kuramoto model in this case? So,
well, again,
it's
because they show phenomenon like a stochastic resonance, or they show phenomenon. A large variety of phenomenon can be captured by a model like the Kuramoto model, okay? If you add ingredients like stimuli, external stimuli, noise, typically, or if you add the complex pattern of a complex network in order to compute in order to take into account the interactions, and we will see this tomorrow, okay? But again, if I have a result, a new result with the Kuramoto model, and I want to implement it in the lab, I will have to use the same idea as I have in the Kuramoto model, but in a different system, in a system that I can implement in the lab. And because of your question, tomorrow I will show you an example. I didn't want to show you an example about this because it was maybe not too close to neuroscience, but I think it's important that you realize when a model is interesting by itself because it displays phenomenon which is interesting, and when a model is important because it's realistic enough, like the Hodgkin and Huxley model, okay? I will add some slide about this duality.
Perfect, thank you.
Okay, so we can close the session and go for lunch, which is time, I guess.
No, we come back 3:30 for the presentation. No.
2:30.
The next session and then the presentations.
Okay, thank you very much.